we will talk about martingale. It is one of the important random processes, and one of the pioneer of this process is Joseph L. Doob, a famous American mathematician. In the case of Markov chain, we exploited the conditional independence between random variables. Martingale uses conditional expectation. So, that is the difference between these two processes. In the case of martingale, we exploit the conditional expectation between random variables. We will start with the definition of conditional expectation. Let us recall the definition. The conditional expectation of a random variable y given x is equal to small x is defined by this relationship. If x and y are continuous, then in the case of it is integration y conditional PDF of y given x dy. So, this is the definition for a conditional expectation of y given x is equal to x when x and y are continuous. Similarly, when x and y are discrete, in that case, this is defined by the sum, that is y p y x. This is the conditional PMF of y given that x is equal to small x, and where y belongs to the range of y, because y is a random variable, it will have some range. So, for all those y we have to consider this sum. So, that way we define the conditional expectation, and similarly we can define conditional expectation of x given that y is equal to small y. There is an interpretation of conditional expectation which makes it practically very useful. Let us see this interpretation. Given x is equal to small x, the best guess for y under the minimum mean square error criterion is E of y given x is equal to small x. Suppose we have an observation small x and y is a related random quantity, and we want to guess what is the best value for y. Now, we can get this. Suppose this guess will be a function of x, so that way we will consider, suppose this is the guess for y. Now, what we want to do is that minimize y minus x hat of x. So, this is the mean square error. Now, this is the this we have to minimize with respect to all the possible function x at x. So, minimize this with minimize this function over all possible x hat of x. So, if we carry out the minimization, then we arrive at this relationship that base value of x at x optimum is equal to E of y given x is equal to small x. So, therefore, if we have observed x, then what is the best guess for y? That is the conditional expectation. That is why conditional expectation is very important. And when I plot, suppose this conditional expectation as a function of x, because it is a function of x, this is known as regression of y on x. Conditional expectation as a random variable. Note that E of y given x is equal to x is a function of x. So, therefore, using this function we can define a random variable gx that is equal to E of y given x when this part is random. So, all possible values of x if we have to consider, then this is a function of a random variable, and that way conditional expectation will be now a random variable in terms of x. We can similarly define conditional expectation. Here we have defined conditional expectation of y given x, but we can define conditional expectation of a random variable given multiple random variables. Suppose E of y given z x, similarly e of x n plus 1 given xn minus 1, xn minus 2, etc. Because these definitions are important for us. Now we will discuss one important theorem, what is known as the total expectation theorem. Now it states that expected value of E of y given x is equal to Ey, because E of y given x is a function of x. So if we take the expectation with respect to x, then we will get Ey. Proof, we will prove this. E of y given x by definition, because that outer expectation is with respect to x, therefore we will write it as integration fx of x dx of E of y given x is equal to small x. Now this quantity we can write as integration from minus infinity to infinity y f of y given x at point y dy, then this is fx dx. Now this quantity, suppose if I separate out this dy dx, now we have the product of fx of x and this conditional PDF. Now this quantity is nothing but the joint PDF. So that way we arrive at double integration of y into joint PDF at xy dy dx. Now note that there is no function of x, therefore we can integrate with respect to dx this quantity, and that will give us the marginal density fy of y, and what we are left with y fy of y dy, that is equal to integration of that over minus infinity to infinity, and that is equal to E of y. So what we have observed then, expected value of conditional expectation of y given x. So this is a random variable. If I take the expectation of this with respect to x, then I will get E of y. So this is one important result. One similar result that we will be using later on. Now here conditional expectation with respect to two random variable. So E of, again this is conditional expectation of y given zx. So but this one is conditional expectation with respect to x. Therefore what we can say that conditional expectation with respect to x of conditional expectation of y given zx is equal to conditional expectation of y given x. So this is the result we will establish, and later on we will use this result. Now let us first E of y given z x. So for a particular value of z and particular value of x, this can be written as the integral minus infinity to infinity y small y and then conditional PDF into dy. Now we know that conditional PDF is joint PDF by marginal PDF. So that way we have this joint PDF fyzx at point yz x divided by the marginal PDF, which is nothing but the joint PDF of z and x. Now we will write this expression. So this conditional expectation now, E of y given z is equal to small z, x is equal to small x, given x is equal to small x. So what we will get, because now it will be conditional expectation in terms of x. So that way and this term is a function of z and x. So that way now conditional PDF will be that is conditional PDF of zx given x is equal to small x. That way we can write. So what we have established, so this quantity into this conditional PDF and then integrate with respect to z. So this is the conditional expectation. Now we will substitute this quantity, that is equal to integration of y, this is joint PDF at y zx divided by f zx of x zx dy into this conditional PDF. So, we have used this relationship here. Now, we will bring dy this side and then carry out the manipulation. We see that f z x given x is equal to x, that we can write as f z x at z is at point z is z x divided by f x of x. So, that this and this will get cancelled. So, what we will have? This term integration y, this joint PDF divided by f x of x dy dz. Again we see that this term, there is no other term involving z, therefore we can integrate this term with respect to z, so that we will get the marginal PDF of marginal PDF f y x. So, that if we integrate this quantity with respect to dz, what we will left with? F y z of at point y x. So, that is what we have written here, divided by f x of x. Now, only one integral dy. So, that way this is the result, and this is nothing but the conditional PDF. This quantity is conditional PDF f of y given x at point y. So, if we integrate y into this conditional PDF with respect to dy, then we will get e of y given x is equal to small x. Okay. Now, considering this as a function of random variable, we will get this result e of conditional expectation of y given z x. This given x is equal to e of y given x. So, this is the result we have established. So, with this background, now we will go to definition of martingale. Now, a martingale is a random process in which the best estimate of future value condition on past including the present is equal to the present value itself. So, we know about the past values, we know about the present values, what is the best estimate for the future value. So, if the process is martingale, then that predicted value is the present value itself. This is an abstract model of a fair game. The expected fortune after a bet should be equal to the present fortune itself. So, that is the model of a fair game, because there is a probability of losing and winning half. So, in that case, the expected value, expected fortune after the bet should be equal to the present fortune itself. This martingale is widely used in many engineering applications and particularly stochastic finance, etc. So, that way martingale is a very important process, and here the future prediction is the present value itself. We will now formally define a martingale process. A discrete time random process x n greater than equal to 0 is called a martingale process if for all n greater than equal to 0, E of mod of x n is finite, that is mod of x n has finite average value. Number 2, the conditional expectation of x n plus 1 given x 0, x 1 up to x n is equal to x n. So, this is the important property, the conditional expectation of the future value given the past values and the present value is the present value itself. So, E of x n plus 1 given x 0, x 1 up to x n is equal to x n. So, this is the martingale property. Now, if the equality sign here, there is a equality sign that it is equal to x n is replaced by less than, then x n that is less than inequality. If we replace this equality sign by less than inequality, then the process x n is called a super martingale. So, in the case of a super martingale process, this conditional expectation is less than x n, and if we replace this equality by greater than inequality, then this process is called a submartingale. So, we have defined martingale, supermartingale and submartingale. In the case of martingale, this is exactly equal to xn. In the case of supermartingale, it is less than xn, and in the case of submartingale, it is greater than xn. We will consider one example. Consider the sum process xn and going from 0 to infinity. So, here we define xn is equal to summation zi I is equal to 1 to n for n is equal n greater than equal to 1 and x0 is equal to suppose 0. Now, we have to prove that this xn is a martingale. So, how do I prove? So, we will prove this. So, we see that x of n plus 1 is equal to summation zi I going from 1 to n plus 1. So, this I can write, because I can write this as summation up to n, then it will become xn plus z of n plus 1. So, what we have written, x of n plus 1 is equal to summation zi I is equal to 1 to n plus 1, and then this is equal to I can write zi I is equal to 1 to n plus z of n plus 1. So, that way I get that xn plus z of n plus 1. Now, let us find out the conditional expectation of xn plus 1 given x0, x1 up to xn. Now, we have a sum, therefore, it will be conditional expectation of this sum given these random variables. So, now first one we can write E of xn given x0, x1 up to xn plus E of zn plus 1 given x0, x1 up to xn. Now, in the first case, because we are given xn, therefore, expected value of xn will be xn itself. And second case, now this z of n plus 1 is independent of all past values, okay, because this quantity x0, x1, xn, they are function of z0, z1 up to zn. So, in that way, z of n plus 1 is independent of this quantity. Therefore, we can write it as E of z n plus 1, and this quantity is 0. E of zn is given to be 0. Therefore, this is equal to xn. So, therefore, if we have a suppose sum process where each increment has 0 mean E of zn is equal to 0, and they are identically distributed, independent and identically distributed, in that case this process will be a martingale process. Now, here zn is 0 mean, suppose instead of that zn has a constant mean mu not equal to 0. In that case, xn is a supermartingale if mu is less than 0 and submartingale if mu is greater than 0. So, that way this example, in this example itself, if zi's are suppose non-zero mean, in that case it can be either submartingale or supermartingale. If mean is greater than 0, then it will be a submartingale, and if mean is less than 0, it will be a supermartingale. So, we gave the example of martingale, supermartingale and submartingale. We will consider another process. Consider the product process xn and going from 0 to infinity given by xn is equal to product of zi I going from 0 to n, suppose. Zn is a sequence of IID random variables, suppose, and we assume that E of Zn is equal to 1. So, each of Zn has the same expected value 1, non-zero expected value 1, and x0 is equal to 1. So, in that case, we can write x of n plus 1, that is equal to product of I from I is equal to 0 to n plus 1. Then I can write similarly like in the previous case, x of n plus 1 is equal to product of zi I going from 0 to n plus 1, that I can write as product of I going from 0 to n zi into zi. Now this is my xn and this is zi. So that z of n plus I. No, z of n plus 1. This is z of n plus 1. So if I take the conditional expectation now, E of x n plus 1 given x0, x1 up to xn. Now that will be conditional expectation of xn into z of n plus 1 given x0, x1 up to xn. Now there are two product of two terms, and we know that z of n plus 1 is independent of xn. So that way we can write E of xn given x0, x1 up to xn multiplied by E of z of n plus 1 given x0, x1 up to xn. Now I know that given xn, this quantity will be xn itself into E of z of n plus 1. Now z of n is a sequence with unity mean, therefore this quantity will be 1. So we will get xn itself. Therefore this sequence xn product sequence, which is a product of IID random variables with unity mean, xn is a sequence of product of random variables with unity mean, then this sequence is a martingale. So we saw that the sum process as well as this product process are martingale. Next we will define what is known as dupe type martingale. Consider two discrete time random processes xn, n greater than equal to 0 and yn, n greater than equal to 0. Then this process xn is called a dupe type martingale process with respect to this auxiliary process yn, n greater than equal to 0. If for all n greater than 0, this sequence xn sequence has finite absolute mean E of xn, E of mod of xn is less than infinity, and E of xn plus 1 given y0, y1 up to yn. This is with respect to that yn process, E of xn plus 1 given y0, y1 etc. up to yn is equal to xn itself. So this is the definition of dupe type martingale. And now we will give one example. Suppose the random process yn is given by yn is summation zi is a symmetrical random walk process, and y0 is equal to 0. That yn itself is a martingale process. Then the random process xn is equal to yn square minus n is also a martingale with respect to yn, n greater than equal to 0. So now because symmetrical random walk, so in that case this is a sum process with average of the increment 0, therefore it is a random walk process. Now we are considering another process xn, which is equal to yn square minus n. We have to prove that this is a dupe type martingale with respect to yn. Let us see the proof. X of n plus 1 is equal to, by definition, yn plus 1 square minus n plus 1. That is equal to, now we know yn plus 1 is yn plus zn plus 1 whole square minus n plus 1, minus of n plus 1. Now this whole square we can expand yn square plus zn square plus twice yn into zn plus 1 minus n plus 1. Now we have to take the conditional expectation of E of x n plus 1 given y0, y1 up to yn. So that way we will get E of yn square given y0, y1 up to yn, E of zn plus 1 square given y0, y1 up to yn, and like that this quantity twice of E of yn into zn plus 1 given y0, y1 up to yn, and minus this quantity. Okay. Now given y0, y1 up to yn, E of yn square will be yn square itself. Similarly, E of z 1 plus 1 square, because we have considered a symmetrical random walk process which takes 1 with probability half and minus 1 with probability half. So that way this E of Zn square, Zn plus 1 square is equal to 1, and now Yn is independent of Zn plus 1. So that way we conditional expectation of the product, we can write that it is conditional expectation of Yn into E of Zn plus 1, and conditional expectation of Yn, given Yn is Yn itself, and E of Zn plus 1 is equal to 0 minus n plus 1. So that way we will get Yn square minus n, that is equal to xn. So therefore xn, n going from 0 to infinity, is a dupe type martingale. So we gave an example of dupe type martingale. Next we will discuss properties of a martingale process. Now there are different interesting properties. First we will prove a simple property, that martingale has a constant mean. That is, if xn is a martingale, E of xn is equal to constant for all n. For all n. How we can prove this? We know that since xn is a martingale process, therefore what we will have, E of xn plus 1 given x0, x1 up to xn is xn itself. So taking the expected value both sides now, because this is a conditional expectation. Now if I take the expected value of this, what we will get, that is E of this quantity is equal to E of xn. Right hand side will be E of xn, and this left hand side will be the expectation of the conditional expectation. Now we discuss about the total expectation theorem. So according to that theorem, this conditional expectation will be E of xn plus itself. Therefore E of xn plus 1 is equal to E of xn. So x of n plus 1 and xn have the same mean. So continuing in the similar manner, we can show that E of xn plus 1 is equal to E of xn is equal to E of xn plus 1, etc. up to E of xn x0 is equal to a constant. Therefore what we have proved, that E of xn is constant for all n for a martingale process xn. So this is the constant mean property of martingales. Let us summarize the class. So like Markov chain which exploited conditional independence, martingale exploits conditional expectation. And one important result we saw that E of y given x is equal to x is the minimum mean square estimation of y given x is equal to small x. Therefore this conditional expectation is important because it directly gives the minimum mean square estimation, and it is used in prediction. Also we see that conditional expectation of y given x is equal to x is a function of x. Thus it defines a random variable E of y given x. And also we studied the total expectation theorem, that is E of y given x is equal to E of y. Next we define martingale. A discrete time process xn is called a martingale process if for all n greater than equal to n, E of mod of xn is finite, and E of xn plus 1 given x0, x1 up to xn is xn. So conditional expectation of future value given values up to present is equal to present value itself. If the equality sign is in this expression is replaced by less than inequality, then xn is called a super martingale, and if it is replaced by a greater than inequality, it is called a sub martingale. So we know the definition of super martingale and sub martingale as well. Now we define another type of martingale process, what is known as the dupe type of martingale process. A random process xn n greater than equal to 0 is called a dupe type Martingale process with respect to an auxiliary process yn n greater than equal to 0 if for all n e of mod of xn is less than infinity, that is finite, and conditional expectation of x of n plus 1 given y0 y1 up to yn is equal to xn. So, then we started with one interesting property of the Martingale process, that a Martingale has a constant mean. What does it say? That E of xn is equal to constant for n greater than equal to 0. Thank you.